Hi, everyone. Welcome back. So on behalf of the Russell Sage Foundation, the Alfred P. Sloan Foundation, and Princeton University, it's my pleasure to welcome you back to the Summer Institutes in Computational Social Science. A big welcome to everyone here in Princeton, everyone at the partner locations, and everyone tuning in on the live stream. It's my pleasure to introduce our speaker for today, Justin Grimmer. Justin is a professor of political science at Stanford University. In fact, you all have already spent some time talking about his work yesterday. Some of his work about statistical analysis of text data. So there was some discussion about this paper called Text as Data, which was one of the first papers of Justin's that I read, and I just totally loved it. That was a paper he did with Brandon Stewart, and that is a paper that they are turning into a book. I guess it's not really turning the paper into a book, but you can imagine a very fruitful paper leads to a wonderful book, and that will be co-authored with Brandon and also Molly Roberts. So in addition to his work about text, Justin also does a wide range of things with machine learning in the social sciences. So he also has a very nice paper about treatment effect heterogeneity and the effect of heterogeneous treatments. It is a complicated title.
It is, yeah.
But it's a cool idea and a cool paper. And so now it is my pleasure to welcome Justin.
So, thanks, Matt, and thanks for having me out. And as we get started, feel free to interrupt me at any time you want to argue, disagree, just yell at me. Okay? Great. Okay, so I want to talk to you today about a project that's largely done with my now former grad student, Christian Fong, who's off to University of Michigan to be an assistant professor. And the title, Causal Inference with Latent Variables, really comes down to our interest that we've had for a long time now in trying to understand how to make causal inferences with text-based treatments. There's a whole bunch of places where this crops up. So for example, in survey vignette experiments, we will often deliver some message to some survey respondent, and we want to see how that perturbs them relative to some other message that they might receive. In general, we might run messaging experiments in either industry or in the social sciences. We may want to see how certain persuasive messages induce people to perform some activities. And of course, the classic version of this, whether within politics or in marketing, is advertising, where we provide some message or some images to someone, and we want to see how they respond to those things. The critical thing that I want to convince you of today, and in fact, if you walk away from this talk either believing me or arguing with me, it would be about this core conclusion. I'm going to argue that the goal in all of these instances is to measure the causal effect of a latent feature. And that's going to be distinct from how we might think about other experiments. The key thing that we're going to be thinking about here is that we want to measure the causal effect of some underlying characteristic of the text. But we have this problem that we can't directly randomize that. Rather, we can write down some words, and we can hope that those words randomize that latent feature. And this is going to be a problem because we have this detachment from the latent thing we want to randomize and the way in which we can do the actual randomization. And what I'll show, and that what we'll prove, is that in a large number of settings, is that the causal inference of text-based treatments is going to rely upon an exclusion restriction. That is, we're going to need to be able to partial out the latent treatment of interest from other features of the text. And that this is going to be true even in vignette experiments. In fact, in the standard vignette experiment, we may be concerned that our latent treatment will depend upon some background text, or we have varied more than just the latent treatment of interest. And I'm going to show you that we can make some perturbations to the normal vignette experiment in order to come up with sensitivity analyses. And what's more, I'll show you that we have to exercise particular caution when we're using machine learning methods in concert with causal inference goals. That is, when we're both measuring the treatments that are present in a text and inferring their effect. One could imagine this could come up, for example, in a campaign setting where you have advertisements being distributed. And in those advertisements that are being distributed in the campaign setting, you may want to infer something about the topic of the ad and then see how that affects a respondent. And what I'm going to show you is that there's going to be problems that show up. The big name for the problem is going to be the very catchily titled fundamental problem of causal inference with latent variables. It's an improvement over the previous name for this that we had, which was called analyst-induced SITFA, which was the distinctive marker of having an abbreviation nested in an abbreviation, which is a career goal achieved. In the fundamental problem of causal inference, what's going to happen is that in the most general setting, it will leave the properties of our estimators undefined. It's not that it's going to induce bias, it's that we can't define bias. But even if we then restrict ourselves to a way in which we could define bias, I'll provide some intuition for evidence about why this problem could lead to biased estimators. Or if you put all those aside, you don't believe any of those assertions, I'll hopefully convince you that if we are both measuring the treatments and inferring their effect, we are in a situation where we can do fishing in a way that had never been done before. And by fishing, I mean searching for specifications that give significance, and therefore leading us to have misleading confidence intervals that won't have the advertised coverage rate. All right, so how are we going to address this framework? Well, I'm going to describe a framework that Christian and I advance in a paper currently under review. The experimental framework is going to address these issues. So the first thing, one way we're going to address this is with a train test split rather than a pre-analysis plan. And this has been, this idea of using a train test split within an experiment is something that's come up a lot recently in a number of papers. And so we're going to use this for a number of reasons, including to increase the credibility of what we're doing and to avoid that fundamental problem of causal inference. I'll also try to convince you that even in a standard vignette experiment, and we're not quite running a standard vignette experiment, that you'll want to construct multiple vignettes per latent treatment in order to avoid those issues that I described before. And then finally, I'll explain how our framework enables the simultaneous estimation of treatments and their effect. And so the idea is that our framework is going to combine both discovery and the estimation of effects. In order to show you how this works, I'm going to apply our framework to infer the features of Trump tweets that gets the public to react a particular way. All right. So why might we be thinking about this? I think this is really part of a broader project that I'm engaged with, that Matt mentioned, this book project with Brandon and Molly. And causal inference with text is just part of what's been going on, which is an incredible interest in using text in order to make a number of inferences. And in particular, these tools have been used for measurement. And the idea is that we can take text and we can reduce it down to some either latent space or clusters, and this has enabled inferences that had previously been impossible. And part of the excitement is that this brings together constituents from a number of different disciplines. I mean, look around the room, I met with a number of you today, and this is truly an interdisciplinary exercise. And the big contribution of this, I think, eventually will be in understanding the causal effects of text. But with anything, when you have these increasing interests, there's also going to be new concerns. For example, there's been an increasing prevalence of experiments, and so we might have concerns of their validity, some of which I want to discuss today in some related work. So one thing we might be concerned about is the credibility of experiments. That is, are the experimental results that I'm reporting truly having the confidence intervals that I've described, or are these the result of running a number of additional experiments and selective reporting? And I'll also show you and explain why we might be worried about extrapolation. That is, the single vignette we might run may not support an inference to a much broader set of treatments, and nonetheless, this happens a lot, and I've certainly been guilty about that in my own work. A thing that I'm not going to describe, but a thing that I think is very important to think about with experiments and thinking about validity, are concerns about how to think about what equilibrium the survey vignette is happening in. So there's a wonderful paper by Ethan Bonademesquita and Scott Tyson where they describe the difference between an experiment and an ideal experiment and the actual experiment. And I think having this in the background is important for thinking about survey experiments in general. We'll try to be attentive to it today. Okay, so enough wind up. Let's go through and let's set the stage for what will be the running example. And then having set this running example, then we'll dive into some research about how we might do this research. Okay, so the big question that I want to try to answer today about social science work is what features of Trump's rhetoric cause a reaction, and what kind of reaction does it cause? Right? This is a thing that we might care about for lots of reasons, in particular because he's president and has a huge audience. But we might also be interested in this to test theories of presidential influence. So the framework that Christian and I advance is a sort of blend of A/B tests with more traditional vignette experiments. One way to think about what we're going to be doing is that we're going to be extracting the features of a message that drive a response in A/B tests. So what do I mean by this? So just so we're all on the same page, in case you've been living under a rock, This is the primary way the President of the United States communicates to the public. And that's not meant to be hyperbolic or critical. It's just a statement of fact. He's got an incredible Twitter audience. So here's an example where he's imputing Adam Schiff, a member of Congress, and lumping in with a group of other people who have been critical of Trump. All right, so how might we begin to think about reactions to Trump tweets? So living in Silicon Valley, this is if I walk down the street and talk to an engineer, this is what they would tell me to do. They would tell me to run an A/B test. The A/B test might look something like this. Tweet 1 would be a classic, perhaps the best tweet the president has ever sent. It is trolling on so many levels, it should be in a museum. He says, why would Kim Jong-un insult me by calling me old when I would never call him short and fat? Oh well, I try so hard to be his friend, and maybe someday that will happen. It's just, anyways. On a lot of levels, you know? Okay, and then I want to compare this with tweet 2 that he tweeted out shortly after Steve Bannon left his administration, where he says, Steve Bannon will be a tough and smart new voice at Breitbart News, maybe even better than ever before. Fake news needs the competition. Okay, so here is a comparison of tweets. What we might do if we were working in industry is we might randomly assign some people to read tweet 1 and then other people to read tweet 2, and then we might assess their reaction to those tweets. And we might even then be able to optimize the tweets that we'd want to deliver to do something like increase engagement or view other political behaviors. So if we observe those differences, not in biographies, but in the tweets, we can make an inference and we can even maximize, like find the tweet that gives us the best response. But of course, this is the problem that makes it very difficult to generalize to the underlying latent features of the treatment that drive the response. Right? So that's one component of an A/B test, but it makes it hard to know what is it about the message that leads people to have a particular response to that. Here's a second thing that we might do, which perhaps is the most obvious thing to do if you're thinking about a document term matrix and text data. So in the first tweet, we might leave this word fake in. And in the second tweet, we might delete the word fake. And then we might run an experiment where we randomly assign some people to read tweet 1 and then assign other people to read tweet 1 prime. And we might observe the differences. And so this is about the causal effect of a single text. Everything. Yeah.
Just gonna adjust the mic a little bit.
Yeah. Okay, sorry.
No, it's good. It's a great talk.
Thanks, Matt. It's the kind of like mid-talk affirmation that I really strive for. It's like the inverse of an econ talk, where they like tell you that you're a bad person halfway through. Yeah. Okay. So again, the setting here is that we might just want to change one word. And the thing that I want to push you to think about is that it's definitely true we could change one word, but often it is the case that we are not interested in varying just one word. In fact, I'd say it's rarely the case that we're interested in varying the effect of just one word. Rather, we could note that these two tweets deliver very similar messages regardless of whether Trump calls the news fake news or not. And what's more, even if we vary just that one word, we should be cognizant that the variance of that one word will be highly dependent on the background text. And by that, I don't just mean that fake is modifying news, but I mean that there's a surrounding context to that tweet. And so one could imagine that you could get very different reactions depending on who Trump is calling fake. So for example, the other day, he was highly critical of Fox News and its polling unit. He didn't call it fake news, but he was very skeptical of what they're up to. One could imagine that's a very different reaction that could lead to a very different reaction from partisans than a similar tweet that's delivered about MSNBC, for example. Okay, so this leads us to this standard setup that we usually see in these settings. And so here we have two different tweets. The first is a tweet that Trump actually sent out. It says, negotiations on DACA have begun. Republicans want to make a deal and Democrats say they want to make a deal. Wouldn't it be great if we could finally, after so many years, solve the DACA puzzle? Then he writes critically, this will be our last chance. There will never be another opportunity. March 5th is this implied deadline. And so one could imagine an alternative tweet where we could vary this critical passage. Negotiations on DACA have begun, yada, yada. And then instead of saying this will be our last chance, we could say, I will use my office to negotiate a fair deal for the Dreamers, March 5th. And so a very standard vignette experiment, at least within political science, is that we could randomly assign some people to read tweet 1, some people to read tweet 2. We might call tweet 1 the brinksmanship treatment and tweet 2 the fair deal for a group of people treatment. But I want to convince you of first is that what we've done in assigning these treatments is that we've made an assertion about a latent representation that's present in the text. That is, we essentially have a code book that we're using. We're saying that all of the words that are different in treatment 1 in this first tweet can be reduced to a single number, we might call it a 1, and that all of the words that are different in the second tweet can be reduced to a 0. And then we want to offer a label for that latent treatment. And that label, in this case, I just described one label we might describe, which is brinksmanship or some negotiation for a group. But we could imagine lots of other texts that could lead to this same label. Now this feature, that we have some code book where we're going to map from the text down to some latent representation, that's going to be true regardless of how you construct your messages in a vignette experiment, whether it's from hand coding, from a supervised method, or an unsupervised method. You're going to have some way in which you're distilling the content of this text down to this latent representation. And as I mentioned, there's going to be many different ways that we can think about delivering this same latent treatment. And we have this other concern, which I think is a real one, that we may change more than the theoretical treatment of interest. So if you look at the differences between these two treatments, one thing that might pop out is the use of dreamers, which is largely used by Democrats, almost never used by Republicans. And this use of fair deal, which could provide different sentiment about what's being expressed here. So we can imagine there's not just informational content that's varying, but also how it's said. And these adoption of labels could lead to differences. And those differences, unfortunately, are going to be aliased if we only have one treatment. All right, so what are we to do? So this simple exercise suggests there's a number of things that we should be really worried about. So the first is that we can't randomize directly on a latent treatment. We need a code book to map from the text to the treatment. We could have effects that depend on the background text, and then more than the treatment of interest could change. In addition to this, we have a whole bunch of credibility concerns. Okay? So what can we do? Well, perhaps we can address some of these with a pre-analysis plan. And so now I'm going to break a bit from the paper with Christian to talk about some work I've done on pre-analysis plans. One reason we might think about using pre-analysis plans is that they could enable us to define that code book beforehand, so we can know what we're going to get into. Perhaps they provide a procedure for determining vignettes, and we can think very carefully about what that background text is going to look like. And perhaps even we could use a pre-analysis plan in order to run some pre-tests in order to minimize the effect of this background text influence. And beyond that, pre-analysis plans give us a lot of hope that perhaps we can use them to limit credibility concerns. So just so we're all on the same page, I want to define what a pre-analysis plan is. So in a pre-analysis plan, the idea is that before we do any sort of experiment or analysis, we're going to declare a plan. And in this plan, we're going to make very clear everything that we're going to do in our analysis. That is, we're going to declare all hypotheses, we'll specify all coding rules, we'll declare all statistical procedures, and we're going to commit to reporting the results of everything that's pre-registered in this plan. The reason that this is a useful framework is that this essentially provides an algorithm that we can use. We take our results, plug it into our algorithm, and take our data, plug it into our algorithm, and out's going to come some results. And if we do this and report all our hypotheses and all our results, then there's no sense in which we fished or overfit or that we should be worried about not the credibility of things like our confidence intervals or our p-values. They will perform at the advertised rate. We could have false discovery rates still. I mean, that's obviously still a problem. But regardless, you would not have to worry about specification hunting. And so I just want to emphasize, because I'm about to be a little critical of this, that there's nothing in what I just described here that's not an incredibly useful framework. If we adhered to this, it would be great, all right? But one question we might have is what actually happens. So this is part of some ongoing work with a grad student collaborator, Apurva Lal, and Jonathan Renshin. And in this work, we analyze what goes on with pre-analysis plans in two directions. We go from the plans to papers, and then we go from papers to plans. And so I'll present some initial results from this work. So one direction we might go is we might go from pre-analysis plans to see what happens in papers. And so to do this, we go to eGAP. And some initial work went to eGAP. And from eGAP, we grabbed some pre-registration data. That is, we got things like the title, link, year, and authors on pre-registered plans, where these things are publicly posted. And then we also look at the content of these pre-registrations. That is, we count the number of written hypotheses, and then the number of hypotheses implied by the statistical tests. Then, where possible, we hunt down the paper. And when we can find the paper, either an online working version or a published paper, we collect data on the journal, the title, whether they link to the pre-analysis plan. But then in the content of the paper, for what I'm about to present to you, we look at the number of written hypotheses and the number of statistical hypotheses. And so before I show some results comparing the hypotheses and pre-analysis plans to the hypotheses and papers, I just want to say that doing this comparison was an incredible effort. The undergrad RA that I worked with on this and I revised our coding rules time and again because it was just so hard to align the two. And eventually we came to the conclusion that that was actually a result, that it was so hard to do this. It's very difficult to align what's going on with the pre-analysis plan to what's going on in an actual paper. And so one thing we can do with this sort of result in this preliminary data is compare the number of hypotheses that are written down, that are described in a pre-analysis plan, to the number that actually show up in the paper as written down. And so one concern we might have is that if we don't actually report all of the results from the pre-analysis plan, is that we've just moved fishing back a step. And we have perhaps some evidence for this in this plot that I'm showing you here. On the horizontal axis, I have the number of hypotheses that are written down in the pre-analysis plan. And on the vertical axis, I have the number of hypotheses that are written down in the paper. And on that line that you see there is a 45-degree line. Ideally, we would see those, that all the dots along that line. That would mean everything that's recorded in the pre-analysis plan is reported in the paper or the appendix. What we see instead is that almost all the dots are below that 45-degree line, indicating that there are more hypotheses being written about in the pre-analysis plan than are reported in the paper. Of course, this might not be the most charitable way to look at it, so perhaps there are other things we can do. So for example, we could try to look at what's implied by the pre-analysis plan. Here, things look perhaps a little bit better, although the graph can be a bit deceiving because of this one point off to the far right. So in this paper, they did a very clear job of identifying every possible heterogeneity that they might be interested in. So while it looks ridiculous that you might pre-register 170 hypotheses, if you look at the actual pre-analysis plan, it's not that crazy. But here again, we see some evidence that there's this selective reporting happening between the pre-analysis plan and the paper. Okay, so we might want to go in the other direction then. And again, this is very preliminary results. And so what we did here is that we looked at the last 5 years of data from top journals in political science and economics. And we scraped all their content, and then we did a simple search for pre-analysis plan and variants of pre-analysis plan in those articles. And there we found 31 articles that mentioned something like pre-analysis plan in the article. Of those, we then manually confirmed 26 claimed to have used a pre-analysis plan. Okay, of those 26, we wanted to try to get a measure of how easy it would be to go back and see the pre-analysis plan. One could imagine that this would be pretty key to having the pre-analysis plan work as a sort of regulatory device. If it's very easy for me to access it and to make the comparison, then I can hold an author accountable for what they wrote down in a pre-analysis plan. If it's hard to hunt down, then it just creates a little friction and it would make it harder for me as a reader of the paper or a reviewer to see that link. And in fact, what we found is that there's less than half, 12 of the 26 of those papers linked to the pre-analysis plan. One link didn't work because of a defunct personal website. As someone who has moved twice in the last 2 years, I can be sympathetic to defunct personal websites. 12 of the 26, so this is less than half. And then in the article, the pre-analysis plan tends to not be mentioned all that much. So about 2.7 times. And the modal pre-analysis plan mentions it once in the text and then once in a footnote, if you look at location of the mention. Yes?
Is there any impression that this is improving over time? Can you repeat the question?
Absolutely. Yeah, so the question was, is this improving over time? So we're working on that. So I want to emphasize, again, that this is preliminary data. But my general impression, qualitative impression, is that it's getting a bit worse over time. So if you look at some initial papers posted in eGap, I'm going to blank on the other authors, but Guy Grossman's one of them. It's a master class on how to do a pre-analysis plan. The footnote at the start of the paper documents everything that's different. And since then, pre-analysis plans I feel like have become a bit of a ritual in running an experiment rather than actually inform the regulatory regime. And so it's gotten a little bit worse. Please.
How do you deal with the fact that a pre-analysis plan might account for like multiple papers? Like there are like different hypotheses for different papers, but one paper is only going to have 3 hypotheses, but the pre-analysis plan had 12 for 4 papers.
Right, okay, so that is a great question. So the question was, how do we deal with the fact a pre-analysis plan could cover multiple projects? And so we looked at this, and our general impression was that the additional hypotheses here weren't coming because this was going to be an analysis that was going to be conducted subsequently, although we can try to link up multiple papers to the pre-analysis plan. That's why I think this direction, though, is the one that would most effectively deal with the objection. If you go from paper to pre-analysis plan, then the idea is we could try to figure out which hypotheses in the paper are actually covered in the pre-analysis plan, and which hypotheses aren't discussed at all, which is a separate problem. And a statistic we're going to calculate is what's the probability if a statistic is reported in a paper, it was actually pre-registered if there's a pre-registration plan cited, which I think would be a bit fairer because of the fact that a pre-analysis plan can cover several projects. Okay. So how do we think about credibility then? How do I think about this? So I'm gonna, Matt told me I could talk about whatever I want. So I'm gonna spend 1 minute talking a bit of a rant, and then I'm gonna go right back into the real research. Okay, so I think pre-analysis plans, again, they're a great institution. It's just very difficult to solve this problem through regulation. Rather, I think we have to solve this problem through incentives. I hung out in Chicago for a year, so that's what you got. So here's the idea that if we made it so that scholars had an incentive to have their work replicated and to have others replicate their work, and to replicate others' work, then I think we'd see a lot more clarity in what's going on in experiments. So if someone said, yes, it's going to be worth your while to publish in a top journal, but it's really going to be worth your while if other people can replicate that result, and other people can get a similar result in similar experiments, then that creates a reinforcement for credibility that's going to be hard to capture with a pre-analysis plan. And the power to do that actually turns out we have the power to do that ourselves. We could decide that that's going to be the standard that we want to impose on the field, and I encourage you to think that way. Okay, end the rant. Okay, so what should we do? Yes, please.
Can I ask a question about the rant?
Please.
I thought that was. I'm glad that you got a chance to talk about, especially what you wanted to talk about. But I wanted to understand. I've heard the idea that we want to create incentives for other people to replicate previous work, and I want to understand a little bit more about the incentives for an author to encourage replication of himself or herself. So, what are the mechanisms that exist for that? So.
Yeah. Okay. So I don't have to repeat this question, right? Yeah. So I think we'd have to create these incentives. And so one way to create the incentive would be to provide a reporting device on a CV to say whether a result has been replicated or not. There is a bit of an incentive now if the journals would publish successful replications, then one would have a lot more citations of your paper if people are able to successfully replicate it. I think, in a way, if you look at citation patterns, the incentive's also there already, because if an experiment's relatively clear, and then you can work with that experiment and extend it, more people are likely to work in that area. And then finally, I think this is a thing, because we're a field that evaluates itself by and large, is a thing that people who write tenure letters could publicly declare that they're going to prioritize. They can say, if you're an experimentalist, I want to see that your work's been replicated. And if you've made it easy for people to replicate your work, this is a thing that I'm going to declare as being important in your tenure file, and I'll write a better letter. So all of those are ways in which we can create incentives. It would take a little bit of movement in the field, and in fact, a great organization like EGAP could do that as well. Okay. So how am I going to think about this instead of a pre-analysis plan in this framework? Well, what I'm going to argue is that instead of pre-registering my hypotheses, what I want to do instead is when I run an experiment, I'm going to do a train test split. And so again, this is an idea that with experiments has been coming up with increasing prevalence. There's been work published in political science, economics, statistics about this idea. So the way we're going to use it in our framework is that we're going to explicitly set aside a random training set for discovery. And then within this training data, we're going to use it to estimate the code book, and we'll see how we'll do that. We'll use it to determine if there are data errors, so we don't need standard operating procedures in this framework. If there are errors, you can just identify those errors. And we could assess other assumptions that might be needed for the experiment. And I'll describe some of the assumptions later. Then in the test data, you will have a single model or a single procedure that you'll use to estimate the data. And because we separate out the training and test set, there's no sense in which the phishing or the recoding that could happen in the training set will affect your inferences in the test set. It's a random split, and if you've truly modeled noise, then you will regress to the mean within the test set. There's a whole bunch of concerns that come up here. I want to preempt a few of them. So one is a power concern. This is the most obvious one. And so I think this is, in general, a real concern. One thing that I would point out is that we want to try to avoid running low-powered experiments anyways. And in particular, if you have a big experiment and you get one shot at it, that experiment should be very well powered, because you don't want to just rely on the unbiasedness. You want to rely upon it being consistent in that case, in which case you should be able to cleave off part of your sample in order to do this sort of split. That's related to this single very expensive. And then, of course, the attentive audience member would say that I'm not making an apples-to-apples comparison of pre-analysis plans and train and test splits. And that's right. So I didn't criticize pre-analysis plans as an intellectual idea. I criticized it as it's been in practice. And of course, we could see similar problems with the train test split. There are ways to render it credible, perhaps. You could think about having experimental data run through a particular organization and then only get to see the training data and then submitting code to run with the test set. But anyone who's coordinated code from lots of people would know that would be exceedingly difficult. Yes.
So we have a question from the live stream. Jacob asks, I've heard at other research workshops that a lot of criticism of pre-analysis plans. I'm not sure I can give the best representation of all those critiques, but I think the nature is that they really constrain the extent to which researchers can modify their research plan, both to change circumstances and also to refine their measures and to better answer their questions. Can you bring up some common criticisms of pre-analysis plan quote-unquote institutions, and why not more scholars are using them?
Okay, yeah, so I'm gonna try to channel what Jacob is thinking about. And it's a great question. And so the usual version of this objection that I hear is something like, when I use a pre-analysis plan, I've removed the possibility of being creative once the data's arrived. Not creative in a negative sense, like I'm gonna go out and hunt for some effect, but I'm no longer gonna be able to recode the data because of some error that's been made by someone who's perhaps working on the data collection, or I'm not gonna be able to notice some really important and very strong heterogeneity in the effect. Or in general, I may not be able to really explore the data when I notice that the hypothesized effect is a null, but there's a whole set of other dependent variables that yield some interesting result. And so in some sense, I think this is right. If we were only going to analyze the results of pre-analysis plans, that would be a problem. But there's nothing in the pre-analysis plan setup that says we can't have some results that are from the pre-analysis plan and then other results that are just clearly labeled off the pre-analysis plan. And so one could imagine a merging of these two procedures, the RANT version, the sequence, and then the pre-analysis plan, where we would start an experiment with something that's pre-registered that we're going to validate from the previous run. And then we would use the second half of a paper to perhaps be more exploratory and to hypothesize some patterns that we've observed. And then we could confirm those patterns in the next round of experiments.
So he's added to this question, one way to ask would be why shouldn't we all run home and register all our hypotheses so we can have more credibility in our findings, and why aren't more scholars doing so?
Okay, so deep down in my heart, I hope most scholars are like honest and want to get the right answer rather than just publish a lot. That would be one thing that could be constraining. And so even if we weren't in that cynical world, it does take a bit of effort to pre-register a hypothesis. I don't think you could just do it out of nowhere. Like you can't just, I mean, you could automate, I guess, all like bivariate relationships you could imagine from experiments. But the world's a big place, and so there's lots of experiments to run. And I think then even a casual observer with a pre-analysis plan could basically see what was going on. So I don't think the institutions failed that much to where we've reached that extreme. Although I don't even think the institutions have failed at all. It's just that there's friction in checking in on the pre-analysis plans. Yes?
You mentioned power and how we shouldn't be running low-powered experiments. Doesn't that kind of, in some ways, incentivize like not doing innovative experiments? Because oftentimes, I know I've run into it, like, I don't know what my power, I don't know how much I need to be powered because my experiment has never been done before. And then I find out that I'm low-powered. But if we're like, you know, prioritizing, like splitting up our samples, we're going to basically just be doing something that has already been done before, so we know how many people have in our sample.
Sure. Yeah, I don't want to overstate the objection to low-powered data. But I also think your objection was not necessarily about low-powered, it was about unknown-powered, right? And so I just push back on it a little bit. I think that we're usually able to ballpark the power of our experiments. Like one could imagine, we discussed your experiment during the speed research ideas. And there you could look to what other researchers have done and at least get a sense of what that power would look like. So if you had to go write a grant in order to run the experiment, you could at least give some sense of what that power would look like. So hopefully this wouldn't constrain super creative experiments. And in fact, I would hope it would enable it because we don't have to be worried about problems in recoding or exploring our data because we know that we'll have a little bit of data once we've collected in order to ensure that we're going to be able to credibly estimate in the test set the causal effect of interest. Okay. All right, so we're going to use this chain test split, and what are we going to do? Well, instead of supposing we know these treatments in advance, what I'm going to argue in this framework is that what we can do is we can include an explicit discovery phase in research. And with that discovery phase in research, what we're going to do is both discover treatments of interest, again in this sort of A/B test-like framework, and then credibly estimate their effect. So we're going to combine these two steps together. I'll show you that it's possible, and we'll talk about some intersections with vignette experiments. So to do this, there's going to be three things that I need to show you. So the first is going to be some theory. And what I'm going to show you is that even though we're randomizing at the text level here, and in fact, every individual's going to either receive their own message or there's going to be many, many different treatments, we're still going to be able to estimate the causal effect of this latent variable, this thing that we can't directly randomize. And the causal estimand that we'll be targeting is the average marginal component effect. This is the same causal estimand that comes up in conjoint. So if you're familiar with Heinmuller, Hopkins, and Yamamoto, we're using that same causal effect. And then I'll describe to you one method for discovering these latent treatments in this framework, and then a method for estimating the marginal effect of those discovered treatments, and we'll apply it to the Trump tweets. Okay, so our causal estimand is the average marginal component effect. And the idea here is that we want to isolate the effect of one treatment averaging over the other treatments. In order to do this, I want to introduce a little bit of notation. So we're going to suppose that we have a vector zi, and this is going to be the binary feature vector for a particular document. It's going to describe the latent treatments that are present or absent in a particular document. We could extend this to something that's more continuous, but we'd have to make a functional form assumption in addition to the assumptions that we make here. So the binary variable is going to be made for simplicity, binary assumption made for simplicity. So the average marginal component effect is expressed like this. We can walk through it. So the first component of the average marginal component effect is going to be an individual's response when component k is set equal to 1 and everything else is set equal to z naught k. The second component of it will be when zk is equal to 0 and everything else is set to z naught k. So for an individual, we can see that we're making a comparison between zk equal to 1 and zk equal to 0. That's the component of interest. And then we're going to hold everything else constant at z naught k. We're going to average over those other z naught k's with this density m, this distribution m. And this is going to describe the correlation between those background characteristics and its analyst set. So if you've used conjoints, and if you do it without restrictions, this is usually a uniform distribution. So you just would weigh all combinations equally. And then finally, we're just going to average over the population in order to get this effect. Okay, so how do we think about this? Well, there's a few ways to think about this. One way to think about what we're going to be doing is we're going to do a conjoint with discovered treatments. Another way to think about this is that we'll be discovering the features that drive responses in A/B tests. Okay, so I'm going to show you that we're going to be able to identify the average marginal component effect. So the idea here is that an individual is going to see a text, which we'll represent as xi. I don't yet have to represent that text in a document term matrix. We can just suppose it's some text that exists. And we're going to suppose that for now that we know what that codebook function is going to look like. So we have some function g that maps from the x to the z. So we take our text, stick it in this function g, and that lets us know what treatments are present or absent. And so we can think about zi as this low-dimensional representation of our text that lets us know what the treatments are. These are the latent treatments. So what are we going to do? We'll assume that there's no spillover, that is, that SUTFA holds. And we're also going to assume the random assignment of texts. And neither of these are going to be too crazy in a lot of applications. So the third assumption is really the key assumption for this framework. So this assumption is an exclusion restriction. And in this exclusion restriction, what we're saying is that the treatment of interest that comes from this g, right, this latent representation, these z variables, is independent of the other text features. And so we could think about assumptions 2 and 3 working in concert. Assumption 2 says we have to be randomly assigning people to texts. Like we can't infer the effect of Fox News or MSNBC based on who goes to Fox News or MSNBC on vote choice. And the third assumption says that if it's the case that systematically, when we vary one variable g, and there's some background feature that's going along with it, we're going to conflate the effect of the z that comes from that g with that background characteristic. So we have to be able to exclude everything else in the text from the latent variable of interest. And then finally, we have to make a common support assumption. And this assumption says that we're going to be able to reach all the treatments that are in the range of G. At first, when Christian and I were working on this, we thought this was a strong assumption. But we've come to think about it as much weaker, because if a treatment is outside the range of G, that is, it doesn't occur within the documents that you observe, then it's not really of theoretical interest to vary that in an experiment. It's hard to know what you're going to learn from that in the experiment. And so the key result that we show in our paper is that assumptions 1 to 4 are sufficient to identify the average marginal component effect for an arbitrary k. So what's going on here, the way to think about this, is that if we know that texts are randomly assigned and we can exclude the latent feature from the background characteristics of the text, we can infer the causal effect of that latent feature even though we didn't explicitly randomize on that latent feature. So this framework, we realized in writing it up, actually applies to the standard vignette experiment. There's reasons why we could think about the standard vignette experiment within this framework. And the way to think about the standard vignette experiment is that we have 1 vignette per latent treatment. Okay? And so in this setting, this is going to require 2 additional assumptions for this to identify the AMCE, when we have 1 vignette per latent treatment. And the reason for this is that because there's no variability, there's ways in which we're going to be able to vary over the population of documents in the full version of our framework, but because you only have 1 vignette per treatment, we need to ensure that that 1 vignette isn't being confused with other things in the text. So the first is that there's a homogeneity effect, that the latent treatments effect doesn't depend on the background text. And that the second is that latent treatments are not aliased. That is, we're not varying more than one thing. And so one reason that you may want to include many vignettes per treatment is that this is going to enable a sensitivity analysis. So in our paper, we show that you can do relatively simple sensitivity analyses where you assess the extent to which your treatments are correlated with other features of the text. It could be like an embedding or a sentiment analysis of the text or other features of the text that you could measure. It is also an interesting problem that because of collider bias, you don't necessarily want to include every feature of the text you could possibly measure. Okay. All right, so that provides the theoretical backdrop. So let's talk about how we're actually going to go about finding this G. All right, so what we're going to do is we're going to assume that we've randomly assigned individuals to read some texts, and we've obtained some responses. And now what we're going to do is we're going to do that train test split. So we're going to set aside a training set in order to discover the G, and a test set in order to estimate the causal effects credibly. And that's going to help us avoid identification issues and overfitting. In the interest of time, I'm going to not talk about the fundamental problem of causal inference with latent variables, but I'm happy to talk about it in Q&A. It's like a favorite topic of mine. If your office is next to me at any point in time, you'll hear me talk about it. Thing I think about a lot. Okay, cool. It's a problem. It's described in the paper. Okay, so now let's talk about how we can go about finding G. All right, so in order to find G, we're going to use a procedure that we first talked about in a 2016 paper that we wrote. For those of you who are familiar with machine learning, you likely know the Indian buffet process. That's sort of a classic machine learning algorithm. In that 2016 paper, we extended it by one word and used the supervised Indian buffet process. The idea of the supervised Indian buffet process is that we take the Indian buffet process, which is the top 4 nodes of that graph, and we added a supervision step. And so what's going to go on here is that we're going to try to discover a G that both explains the document term matrix well, explains the text well, and is going to explain the responses well. So it's going to be making a compromise between those two things. So the idea with this data journeying process is that we suppose that there's some background proportions that describe the prevalence of our treatments. That gives rise to these Z's. And these Z's then simultaneously are attempting to explain the document term matrix, much like you'd expect a topic model to do. So it's a low rank approximation of the document term matrix. And these Z's are also attempting to explain the response. In this case, it'll be the evaluation of the Trump tweets. All right, so in the training set, we're going to use the Indian buffet process in order to discover the mapping from the texts to the treatments. So what we're going to do in any setup where we're using this is we apply the supervised Indian buffet process to the documents and infer the latent treatments that are present in the texts. We're going to do model selection in 3 ways. So first, the supervised Indian buffet process has some built-in model selection. It's non-parametric. This means that it's going to determine the number of features it's going to include automatically. But we should be a bit skeptical of that because it's not solving our particular problem. And so in order to further verify those results, we have a measure of quantitative fit that essentially looks at the cohesiveness and exclusivity of the features that we discover. And then we engage in some qualitative assessment, looking for features that seem to make sense to us. And we're unapologetic about exploring the data here because we're in the training set. We're not going to be worried about overfitting because we're just going to go to the test set next. So once we've done that and we've locked down a particular model, we go to the test set. And there, we're going to use the test set to both infer the treatments that are present in those texts and measure their effect. So the idea is once we have the supervised Indian buffet process, we'll use that, we'll go to the test set texts, and we'll infer the latent treatments that are present in those texts. And then conditional on those latent treatments being present, we're going to use a regression in order to measure the uncertainty.
We have Christina in Chicago just wants to say, backing up for us non-experts, could you explain what the Indian buffet process is?
Totally. Okay, so this is like my favorite story for machine learning algorithms. So the Indian buffet process comes from 2 people whose names I'm going to blank, but someone in the room likely knows who came up with it. Anyone? No? Great. Okay, thanks guys. Okay, so they were researchers in London, and they would go out on the weekend to Indian buffets. And if you've been to an Indian buffet before, you know you grab a plate, and then you can select dishes, okay? And so the idea with the Indian buffet process is that a document is a customer. The dishes are the features. And you imagine the document going down the buffet, and if it selects the dish, right, then that treatment is going to be present in that document. All right, so the idea is that we're either going to have a document is either going to have that treatment in it or not. That's what Indian buffet is going to do. And then we're going to measure those, the latent treatments are going to essentially be like a factor analysis of that document term matrix. Okay. I hope she's nodding her head. It's hard to, you know. Yeah, I know, I gotcha. Yeah, no nonverbal cues, you know. Okay. Great, okay. All right, so we apply this, and so again, we're going to estimate this G that'll let us know if the treatments are present or absent, and then we can use that G in order to infer the treatments that are present or absent in the test set documents. Once we've made that inference, we're basically in a pretty standard experimental setup, and we can estimate the effect any number of ways you want to. So one thing you can do is that you can just run a regression. So you regress the response on the treatments, and then you can estimate uncertainty with a bootstrap. Okay. So we're going to apply this to a YouGov survey on Trump tweets. So this is a survey is a lot of fun, and it's meant to get a sense of how the public reacts to some Trump tweets. So again, this was a motivating example here from Trump about Adam Schiff. Okay, so what YouGov did is they sent out in batches of, I believe, 7, they sent to groups of Republicans, Democrats, and Independents a series of tweets. And in those tweets, they asked people to read those tweets and then evaluate them as great, good, okay, bad, or terrible. All right? And then based on that evaluation, they're going to create an aggregate scale that's going to range from -200, everybody calls it terrible, to 200, everybody calls it great. And so what we're going to do in order to assess this, we'll work at the aggregate level here, and we'll look at the tweet level and compare the reactions of Republicans, Democrats, and Independents. And we're going to modify that supervised Indian buffet process, but now we're going to enable it so that there's going to be shared treatments. So Democrats, Republicans, and Independents have the same treatments in the text, but we'll enable it so that we can, when we're discovering, we recognize there could be heterogeneous effects. So the effect of a Democrat might be different than the effect of a Republican to a particular tweet. And that should help us to both discover treatments of interest while taking into account the differential response of individuals. In order to do this, because of that heterogeneity, we're going to lean heavily on the training set. So we put 2/3 of the data in the training set and 1/3 of the data in the test set. And we're going to cluster our standard errors at the tweet level. Okay. Oh, sorry, not the standard. We're not clustering our standard errors at the tweet level. We're going to cluster this assignment at the tweet level. So we don't have Democrats seeing one tweet in the training set and Republicans seeing one in the test set. So all the tweets are either in the training or the test set. And so from this, we can get a list of keywords that give us some indication of what's going on in those treatments. Again, like a topic model, this is going to be a vector that's going to give us a weight over all the words. Some will be positive, some will be negative. But here I'm just giving the top 10 positive words, and they can give us a sense of what these treatments are about. So for example, treatment 1 is very clearly, and you can confirm this with some manual validation, a treatment about the fake news media. Treatment 2 is about the stock market and a bit about Trump's endorsement of Luther Strange. Treatment 3 is about the effort to repeal Obamacare. And then treatment 4 and 5 are broadly about things that are happening in the world. 4 is about both the NFL and Melania going out in the world, saying prayers, being presidential, sort of figurehead stuff, aside from his criticism of the NFL. And then treatment 5 is about things happening in the world, so broad world events. All right, so we can then use our procedure to estimate the effect for, in the far left of every plot, Democrats, then Independents, and then Republicans. And so what was remarkable to us about this initial set of results is that it would seem that Democrats, Independents, and Republicans all react negatively to Trump doing things like lashing out at the news media. Now, of course, we might be worried that there's other things going on other than the treatments that are present here, and that's part of what makes this a good example. So one of the things that we're able to show in our paper is that it is the case that there's some systematic relationship between the treatments that we discover and the sentiment that's present in the text. And so we show that even once we condition on measures of sentiment in the text, we retrieve the same results. So we conduct our sensitivity analysis and retrieve the same results. And we're able to conduct that sensitivity analysis because we have many treatments per, many texts per latent treatment. We see similar broadly negative results in response to healthcare and largely positive reactions to things like talking about the stock market or events in the world. Okay, so as I mentioned, we did a sensitivity analysis and we get very similar results. And you can actually download this package and use it for your own procedures with the rpackage text effect. Okay, so to wrap it up, so this work that I presented here is part of this book project that Matt mentioned that Brandon and I both declared we are finishing this summer, and so we've, yeah. Yeah, can't tell if that's sarcastic clapping or not, but I'm going to interpret it as, yeah. Thanks. Okay, yeah, it's happening. Okay, and so in this book, we make a number of arguments that are related to what I've made here. So in part, we want to convince more people to use text as data in their research, but we also want to think about the role of things like machine learning algorithms in the social sciences and how that can help us to rethink the way we make inferences in the social sciences. And so what we advocate for in the book, and what I've hopefully spent a little bit of time advocating for here, is a sequential and unapologetically inductive approach to social science, in a contrast to the usual deductive approaches. And the idea is that we can build and refine theory with successive either experiments or observational studies. And part of what goes along with this is a partial redesign of survey experiments or even observational studies. And then the final thing that I want to suggest, and a thing Matt and I discussed earlier, is that one needs a great deal of caution when combining machine learning and causal inference methods. Now, this can range from the subtle issues, which I didn't get a chance to discuss, like the fundamental problem of causal inference with latent variables, all the way to the obvious thing, whereas if you're measuring your dependent variable and then assessing its effect, in the same study, your potential for phishing goes through the roof relative to what other studies can do. And so I think as these methods move into the social sciences, there's going to be a real opportunity both to discover new things and do new exciting research, and to figure out the boundaries of these methods, what they're capable of doing and what they're not capable of doing. So thank you.
All right, so we'll start with a question from the live stream. Rebecca in Chicago asks, did you have to control for previous exposure to tweets? For example, someone who might have read the true tweet previously might have an established sentiment toward that tweet. I'm thinking about some of Trump's tweets that have since been turned into popular memes.
Yeah, so I think that there's a whole bunch of ways to go back to this idea of that there's an equilibrium we have to think about. So not only do we have to think about previous exposure, but there's an evolving sense in which Trump's messages take on different meanings. So like the Bannon tweet now is ironic. The Kim Jong-un tweet is also ironic. There's a number of ways in which Trump has been critical. If you don't follow this Twitter account Trump Hop, I encourage you to do it because you can see what he's tweeting on that day, years before. And so I think these are real concerns. So we didn't have access to previous Trump exposure. And so one of the things we can do, though, is we can rerun an experiment where we can give people sort of fresh Trump tweets. And if we're explicitly randomizing exposure, then we have good reason to believe that we'll be balanced across those tweets. Yes?
I just have my own question on
Please,
top of that.
yeah.
You're talking about like future iterations of the experiment where you give fresh Trump tweets. How do you effectively write, if you're looking for specific latent variables, kind of reliably knowing that like those fresh tweets are going to give you the variables you're interested in?
That's right. So one thing you can do is once you've fixed a G, so if we've, say, take the G from this experiment, we could take the tweet and run it through G. We don't need the dependent variable in order to do that. That's one version of it. Another way to do it is that we could move out of the G that's been automatically discovered, and we can construct our own code book. And we could ask coders to code the tweets and then deliver tweets based on what our coders say. There's other crazier ideas, but those are the two, I think, most sane versions. Please.
So I'm wondering to what extent you could use these tools in cases where participants like generate text. So I'm thinking of either Jamie Pennebaker's research, where they're interested in linguistic features that mediate depressive symptoms, or in Travis Riddle's research looking at self-affirmation exercises. Do you feel like similar methods can be used to determine what are the linguistic features that mediate those beneficial effects, or is it different because it's a person who's generating the text and not evidence of the same?
This is a great question. So how do we think about mediation analysis, where the mediation occurs through text? Okay, so likely there are a similar set of features or algorithms that could be used in order to discover these latent features. I think we'll need even stronger assumptions beyond the ones that we made here in order to sustain the mediation. But one could imagine similar assumptions are being made if you're already using text to do a mediation, and we could still learn interesting things even if those assumptions are strong. And so I think that that's a possibility. We haven't done any of that work yet, so I'm not quite sure what those what those assumptions look like.
Thanks for a really rich talk. I got kind of lost because it's been a really long week already. So just to unpack a couple things. So
Yep.
What's a code book?
Yep.
Why do you use a 2/3 test set split or
Yep.
test train? And how did the test train split influence your analysis at the end? I couldn't quite track that.
Totally. Okay. So the first thing, what's a code book? The idea there, the code book is just like you could imagine a code book if you're giving to coders. It's some rule by which once I have a set of texts, I can map the treatments that we're going to say are present or absent in the text. And so there's a whole bunch of things that are critical about this. So one thing is that it's not in the head of the respondent. We don't have to believe that the respondent is inferring that those texts are present or absent, just like we wouldn't have to believe a respondent's inferring those texts are present or absent if we've declared what the treatments are in a text. Okay, so that's the code book, and we're going to discover it automatically. We did the 2/3, 1/3 because we were really worried about this heterogeneity issue. And so because we were worried about the heterogeneity issue, we wanted to be able to discover treatments even though they varied by group. And so we were worried that we wouldn't have the power to discover these treatments in these relatively short tweets. And so that's how we ended up with 2/3, 1/3. We're still very much in the dark on how to do power analysis when we're running this setup, even though we've done it a ton now. And so if anyone has any ideas, we'd love to hear more about it. And then the train test split was really crucial because in the training set, not presented here, was Christian and I beating up the data, arguing with each other about what the treatments meant, and then like reading the text deeply to make sure that we understood what those treatments were. And then we locked it into place, and then we went to the test set. But so like that was like not pictured as like months of agony, not months, but like a long periods of agony between Christian and me.
So is it fair to say you generated your code book on the training data?
That's exactly right.
And then applied that into those, and that's what the graphs we see are doing.
Exactly.
Okay.
Yeah, and so if you think about like analogs to this, so to me, there's a whole bunch of analogs to what qualitative researchers are already doing. So I think this is an instance where quantitative researchers are sort of behind what's going on qualitatively. So there's of course grounded theory, which is explicitly inductive, and the notion of generating code books using some prior sample and then going to the next sample is a thing that's well grounded in a number of qualitative settings and some survey settings. So we're just moving it here into this machine learning setting.
Thanks.
Like, have you think about how your framework can be like linked to places other than text? Like, because in essence, it's about you have high dimensional observable, but the treatment itself is latent. So maybe like you have many IVs or something like that, but the real treatment, the IV is like a proxy for the real treatment, but you don't really know about the treatment. So I think there are still many like spaces that can extend your framework to like future directions now.
Yeah, so I think one obvious one is images, which image experiments are really difficult to do, and it's hard to know that you varied just the component of the image of interest rather than many other things when folks are presenting different images. So some of the best experiments try to limit that, but then you have to be worried about this extrapolation. So images is one. But one could imagine in settings where you have, on the right-hand side, a lot of data. So it could be like roll call votes, would be like one example, or characteristics of the district, if you're thinking about the effects of gerrymandering. And in these instances, you may want to infer something about these latent treatments, so you could use this like very similar framework.
Thanks, and I like it a lot about your idea that you actually want to discover treatments from text instead of just like relying on researchers' discretion to kind of like believing that they actually measure the latent thing they want to measure. But based on this like point, I want to ask like if it's possible that you actually do some like comparisons between, like, so imagine like you find some treatment from some text, and then for one of the treatments, you just imagine how the common like political science researchers would design vignette experiment using these words like fake news and other stuff, and then kind of compare how the way the treatment effect you estimated from your kind of discoveries versus how a typical vignette experiment would estimate this impact. And I think that could be an interesting kind of sensitive analysis or kind of robustness checks.
Yeah, I agree 100%. So ideally, we'd have a subsequent experiment where we've taken our code book and then we run a randomly assigned tweets based on the treatments present. I agree.
Thanks for the great talk. I have two questions about using the text as the treatment variable. The first one is because the treatment variable is multiple dimensional, so when we are analyzing it, can we consider the false discovery rate or do like multiple testing stuff? And this is the first question. The second question is the unconfoundedness assumption, that is, especially when we are doing observational studies, these kind of assumptions are really hard to justify. So just wonder if how you can give me some advice when we are using it, using the text as treatment variables.
Sure. Okay, so I'm going to take it in reverse order. So the first is about like unconfoundedness with text. So if I'm understanding you, it's about assumption 2, which is about selection. And in those settings, things are going to be always pretty difficult. So one can imagine having some design could be nice. So if there's something that induced people to read more of the news on a particular day, or if there was some other way in which people have been exposed to news that's not related to their background, say propensity to support a particular candidate, that's the usual strategy, or hoping that you have like some set of covariates. So I don't know if that's very satisfactory, but I think it's the same set of selection problems that you'd get everywhere else. Okay, so then the false discovery rate, so that's a real issue here. So we could certainly try to do something to correct the false, that there might be some false discovery here. Though even if we did some correction, aside from doing something very conservative, we'd likely end up with similar conclusions because we have relatively strong effects across there. But one could imagine a perverse incentive that you might have, which would be to create a code book that has 50 treatments, and then use those 50 treatments in order to discover something significant and write the paper just about the things that you've discovered. And there, of course, you'd want to do something important with the false discovery rate. If the other idea, though, is that if we were thinking about the actual text being on the right-hand side, there we don't have to worry about that, again, by assumption, though, because we're supposing the effect of the text is running through those latent features, and that the background features aren't affecting it, so that we know that the text is channeled through these features that we've discovered.
Hi. So I was really fascinated by your discussion of train test splits and pre-analysis plans, and I wanted to ask a question about that.
Sure.
So it seems like as these sort of research strategies have become more popular in the social sciences, part of what we've realized is that is essentially doing the kind of confirmatory causal research that we would like to ideally be doing is a lot more expensive than we originally thought it would be in order to get the kinds of statistical guarantees that we would like to have. Mm-hmm. So given that that's true, do you have any thoughts on sort of like ways that we might rethink the sort of organizational or professional structure of the social sciences to sort of facilitate that?
Yeah, this is a great question because it gives me the opportunity to like dream big and rant. So there are ideas that have been floated that I think are great ideas. So one thing we could imagine is creating consortiums of people who are either located similar geographies or have similar approaches to running experiments. And it would be great one day to have a setup where a political scientist posts an important experimental result and some other consortium that's pooled resources can say, well, we can at least validate this using a survey experiment that we can run very quickly in order to see if we get a similar sort of result. And if we had that sort of shared pool of validation, that would be really great. As far as expensiveness goes, I think this is another real and big concern, and I'm not quite sure what the right mechanism for it is in order to enable people to have shared access. One thing would be continued noting that things like student populations or MTurk actually can perform pretty well on a number of experiments. We could replicate results. That seems to have democratized experiments substantially. But professional organizations distributing more resources to people who don't have access to the kind of grant money so they can run experiments or do the kind of research-intensive work that people at research-rich universities can do. That would also be helpful. Oh, okay.
I was wondering if you could talk a little bit more about the process of going from the test or the train to the test set in terms of how you make that, kind of the mechanics underlying how you make that inference of whether a treatment is present and how much uncertainty there is in that process, and whether the kind of estimates of the treatment effects capture all of that uncertainty, or is it kind of conditional on making the right inference about the presence of the treatments?
Yeah, this is a really interesting question. So we rely upon the model. We don't condition on the dependent variable when we're making the inference, but otherwise we rely upon the posterior of the model to infer the treatments that are present or absent in the test set. So we had originally set up this procedure to bootstrap everything, our uncertainty about the presence or absence of the treatments, and then the uncertainty about the causal effect. It was pointed out to us that if we did that, if we included the uncertainty from inferring the treatments, that we could violate the definition of a function, and that wouldn't be a very good thing in this particular setting. And so we have, for that theoretical reason, we no longer include the uncertainty from inferring the treatments. So this captures the estimation uncertainty from the regression, but not the uncertainty from inferring the treatments. And so in this case, I don't think it matters particularly a great deal. Things seem to be pretty precise in our inferences, but one could imagine that if you're 50-50 on some inferences about documents, then it could matter quite a bit, particularly if those are high leverage documents.
Hey, I was just thinking, you and Brandon, I think of as kind of yin and yang, and he's introduced us to this tool, which is kind of like supervised topic modeling, and you're talking to us about supervised Indian buffets. So I'm thinking, like, when would you advise using one or the other? Because they're both inductive tools for generating features in text that you could use to estimate things, but I don't really see his tool being used in train test split context, and I'm wondering if there's some kind of underlying architectural reason for that difference, or yeah. That's
cool. Okay, so a bunch of answers to this. So the first is that when we designed this originally, back when we were working on this in 2016, we thought we would use supervised LDA, which is in the family of topic models. But it turns out it's very difficult to do the marginalization that I described on a topic model, because it embeds documents into the simplex. And so there's no sense in which you could set like one variable to one value, another variable to another value, and hold everything else constant. It's necessary that those two won't be the same, because everything has to sum up to one. And that's why we then turn to this family of models that enable us to have this freedom. Now there's ways to get around that. There's things that you can do in order to define causal effects there, but we wanted to have this clear causal estimand because we had a lot of other things going on in the paper. So in a separate paper that Christians that has worked on, and Naoki Yagami, Brandon, and Molly, we do the structural topic model with a train test split. And in fact, about a year and a half ago, they pushed an update to the code. And so now in a structural topic model, you can infer a topic model on a training set, and then infer you can train a topic model on the training set, and then you can infer the topics present in a test set. And we use that to do text as a dependent variable. And so in that paper, we provide a set of assumptions to identify causal effects when you're inferring the dependent variable, which provides, I think, a nice companion to their super influential papers and like the AJPS and JAZA on using the structural topic model in experiments. Right behind you.
Thanks for the great talk. I think one of the fundamental insight I'm kind of digesting and trying to think through is, for example, if you think of doing a survey experiment or audit survey, you're assuming that by changing something, usually manipulating text, I could give the project example you provided, we assume that we are capturing some latent concept in the research. And I was just reading the paper at the same time listening to your talk. And one of the key messages in the paper is but actually you're making a strong assumption because you're kind of generalizing from the one treatment about the population you are capturing. So even though, for example, I did a survey that has 1,000 participants, and I spent more money and got a 3,000 participants, but still, actually the problem getting more serious because you are making more strong assumption about the population. So your suggestion is basically, instead of just increasing the N, you also need to think about how you can vary treatments. And so my question is, given that understanding, my question is that maybe it's possible to go the other way. So if you can design a better treatment for the population, maybe you can find a way to reduce cost for running a survey or running research in general. So one of the main change for researchers doing behavioral work or in any kind of work is, it's increasingly difficult to get a good data given the limited budget.
Yep.
So I hope that maybe there's some, whether you have some thoughts about it, given you have new method to find a better measure of the latent concept, whether there are some ideas about reducing cost for doing a research.
Okay, yeah, so your insight into the paper is exactly right. So part of the things that are going on with our assumptions is that we have in parallel assumptions about how participants are selected in the study and then randomized. And then we want to push people to think about the way documents are selected from a hypothetical population of documents. And so then if we're thinking about using this sort of tool in order to refine the treatments, one of the things that I would push researchers to think about is that before you go run the vignette experiment to do in-depth analysis of the way politicians, elites, whomever you're studying actually talk about the issue at hand, this is a thing that I think has come up in a few places in my work, and this is just trying to connect the dependent variable with that. So one could imagine an observational study like that I've done here. There could be problems with it, but one could imagine engagement metrics with Trump tweets or the rate at which these tweets are then picked up by traditional media in order to understand how the content of the tweet is affecting the ways in which people are engaging with the tweet. And then perhaps you could use that in order to focus on treatments that are going to be more effective when you go to the experiment. There's still this issue, though, of we have to make an inference to this population of tweets, but I think that could be helpful.
In some ways, I guess you kind of started answering my question by referring to this as observational research. But what I was wondering is what was the control? But I guess if it's not an experiment, but we're talking about causal, and so I'm used to there being a control when I'm talking about treatment. So what is the control?
Yeah, okay, so this is one of the trickier things about this causal estimand. So the control here, for example, for treatment 1, the control is just when treatment 1 is turned off. And then we're going to vary everything that's going on with 2, 3, 4, and 5. And so when we're defining that estimand, we're looking at what happens when treatment 1's turned on relative to when treatment 1's turned off. And then we're going to fix the values for 2, 3, 4, and 5 to 1 or 0, and then we'll iterate through those. And then we'll average across those according to some analyst-determined set of weights. And so control is like treatment 1 not being on.
It's like a big movement of the microphone for a very quick question. And what is the control in the YouGov survey? What I think I didn't get exactly how you move from the treatment in the original survey to your estimation of the treatment, the latent treatment.
Yeah, this is a really critical point, that there's no traditional control here. So if we're thinking about a control for any one of the treatments, we're making a comparison to when the treatment's turned off. And so when we're running an experiment like this, everyone's getting their own treatment, and no one is getting an explicit control treatment. Rather, we will then infer that there's a control when the treatment's off. And so everyone's being exposed to a message. We're just making this on-off comparison. And so just to finish the thought, if things are highly interactive, then there could be a lot of reasons why you'd expect effects to vary depending on the background features. If things aren't super interactive, if the response to treatment one doesn't depend on the prevalence of everything else, then this linear model we estimated should do a pretty good job.